So let's talk about an application that you might be very familiar with. So center of mass is a topic that you talked about in Calc 2. So in particular, what you were looking for is the center of mass of a thin plate, and usually what we call that is a lamina. So in Calc 2, you dealt with thin plates that had uniform density. So that's kind of what you should have been working with in Calc 2. So here we're going to go ahead and expand that idea to the x and y. So we were just looking at a thin plate with just a function of x. Now we're going to look at a function of x and y. So let's say now our thin plate has variable density. So maybe it's heavier on certain points. So given a thin plate with density in mass per unit area at a point x comma y, we're going to denote our density as rho x comma y, where rho is a continuous function on D. So our rho, our density, is approximately equal to the change in m divided by the change in a. Now, why is that true? Well, if you think about what density is, right? Density is just the mass divided by, well, if we think about it as thin plates, is divided by area. If you think about now like a surface or something like water, you would divide it by volume. But in this case, it's going to be mass divided by area. So if we're looking for our rho, our density, each individual mass, you take all the change in the mass divided by the change in the area, and that will give us our density. Okay, now our goal here is to find mass, and this is going to be super important when we get into our next section, because mass is probably one of the easiest way to kind of think about a lot of these problems. So if we take a look and rearrange this formula, we can see that the mass is just equal to the density times the area. So if we want to find our mass, okay, all we really got to do is divide each of this lamina into little rectangles. Okay, so our mass is going to be adding up each of these densities, right? Each of these little densities and multiplying it by our change in area. So we're taking all of these little areas, multiplying it by our density, and that's going to approximately give us our mass. Now, because this is variable density, we're going to have one in the x direction and one in the y direction. So that's why we have our two summations. All right, so our mass is going to be equal to, if I were to break this up into smaller and smaller rectangles, our mass, and I'm going to write this here, is going to be equal to, so mass is going to be equal to the double integral over the region D of rho xy dA. So this is actually really cool, because we've been looking at double integrals as volume. Well, now it can mean something different. If I have a surface, so let's say this is our surface, and we know what its density is, its density function. If we take our double integral of this density function, right, of the density function of this surface, what we end up getting is the mass of this surface, which is actually really cool. And it's something a little different than how we've been looking at, because so far we've been looking at double integrals as just volume. But now, if we integrate out this density, then what we end up getting is mass. So this is going to be super useful for us in our next section. So let's say we want to find our center of mass. So let's say we have this thin plate, and because there's probably it's going to be heavier on certain parts than others, we want to know where exactly is the center of mass. So in other words, if I had a fulcrum and I just wanted to go ahead and just see where exactly it will be able to balance, we want to find the point at which I can put this fulcrum and I can put this thin plate on top of it, and it'll just balance out. So in order for us to do that, well, we need to find two other things. We need to find the moments. So the moments is the tendency for the lamina to rotate about an axis. So we got to think about the mass, the distance the mass is from the x-axis. So if you kind of think about it as, so let's go ahead and draw it. Here's x and here's y, and let's say you have a thin plate, so something that looks like this. You want to know how, so what is the tendency that it rotates about the x-axis? So basically what we're doing is we're taking from the x-axis, we're taking the distance of every single value here. Okay, So kind of just think about it, the tendency of it kind of rotating. So like looking at all of these values. So the tendency, which is called the moment about the x-axis, all right, notice that if I take a look at the x-axis and see how far each of these guys are, well, really what I'm looking at is the y values, right? So you have a y value here, y value here, y value here. So you're really looking at the distance from the x-axis to every individual y value. That's why you have a y in there. So you're going to take the y value, multiply it by its density to find the moment or the tendency for the lamina to rotate about this axis. So what will be the tendency? We're quantifying that particular value. And similarly, you can do the same thing with the moment about the y-axis. So the moment about the y-axis, you're finding the tendency for it to rotate around the y-axis. So you're taking our y-axis and taking a look at all of the different values that are in this direction. So notice that all of those values correspond with the x. That's why the x is right there. So that's basically what you're doing. So you're summing up all of the how the distance, from the x-axis to every single point here. So that's why we have the y times the density. That will give us the moment about the x-axis. Same thing with this guy, the moment about the y-axis. So we call this the first moment of mass. So how would we find the center of mass? Well, since we have the addition of all of the different distances, all we really got to do is figure out, okay, where exactly is it heavier at? So all we're going to do is just divide it by the total mass. So that's why it makes sense for our center of mass to be the moments divided by m. And now I know that the formulas get really funky here because you start looking at m sub y divided by m sub x divided by m. Well, remember that the moment about the x-axis took into account all the y values. That's why it would make sense to use this guy for the y bar. So for our center of mass for y. And also same thing, the moment about the y-axis took into account our x's. So it would make sense for me to divide all those by the mass from that moment to get x bar. So the way that we say this, oops, that's wrong. The way that we say this guy is x bar, and the way that we say this is y bar. And these guys are just centers of mass. Okay, again, the formula is not pretty, okay? So, but one thing that you can think about is think about averaging the masses. So you're just averaging all the masses together, okay? Alrighty, so now let's go ahead and go here. Now let's talk about the second moment of mass, which is called moments of inertia. So here's where we're gonna steal a formula from our physics friends. So from physics, we know that inertia is a tendency of the mass to resist a change in rotational motion about the x-axis. So inertia in all its entirety, to be able to quantify that is just the mass times r squared, the radius itself. Okay, so tendency of mass to resist a change in rotational motion. So in other words, think about how hard it is to move something, some sort of like thin plate. So if you have a table, right, obviously there's going to be different types of inertia because it's going to be harder for me to lift it from here. Like if this was you, and you wanted to go ahead and lift this, this will be really hard to go ahead and flip it, as opposed to maybe in the center. So that's kind of what the moment of inertia is, kind of like the tendency of the mass to resist a change in the rotational motion. Okay, so how hard is it to flip this guy about a particular axis? So one way that we're going to do it is that, okay, well, how can we calculate inertia? So we know what mass is. We just figured out what mass was. That's just the double integral of the density. That's the mass. And now we're going to multiply it by r squared. So let's say we were multiplying it by x squared. Okay, we were looking about it at the x-axis. So we'll have the double integral over the region d, or r, or whatever it is, x squared rho xy dA. This guy is actually the moment of inertia about the y-axis. And we can also think about it in terms of x, right? We're just going to be moving the x to a y squared, and that will give me the moment of inertia about the x-axis. Okay, if you want to find the moment of inertia about the origin, all you got to do is multiply this by x squared plus y squared, but it would be easier for you to just find the moment of inertia in the x direction and the y direction and then just add them up. Okay, another way that you can kind of think about inertia is kind of think about it as a Ferris wheel. Think about how hard it is to stop a Ferris wheel, because a Ferris wheel has a lot of mass. So and to be able to stop it, right, will require a lot of there's a lot of resistance going on there, so it has a lot of inertia. Okay. All right, now the last topic is radius of gyration. I know that I'm throwing a lot of formulas at you, but radius of gyration, so let's say, for example, our entire mass is located at a particular point. Okay, so making sure that the inertia itself is held the same. So if nothing has changed, what would be the best place to push this particular thing and to make it go around the x or y axis? So we're going to localize all at a single point. So the radius of gyration is basically what that is. The best place to push it to go around the x or the y axis. Okay, or even the origin. And all you got to do is find the inertias, take the square root of the inertia divided by the mass. So the formulas are not great. They're pretty complicated. And we'll do an example right now. Okay, so we've been doing a lot of integrals already, so we're going to go a little bit faster here. So let's go ahead and use the triangular region with vertices 0, 0, 2, 2, and 2, 0 with density rho xy equals xy to find the mass, center of mass, moments of inertia, and radius of gyration. So let's start off first with the mass. And the mass is super easy, and this is something that I hope that you really know. So our mass is just going to be the double integral over the region of rho xy dA. Okay, so now let's take a look at what that looks like. So our region itself is going to be 0, 0, 2, 0, and 2, 2. So this is what the region looks like, okay? And at each point, your density is xy. So you can see that the higher x and y is, the more dense it is. So it's going to be really heavy over here. Over here, maybe not so much, but you know, but then it gets heavier and heavier as x and y starts to increase. So it becomes more dense, right? So what we're going to try to do is we're going to find its mass. So this is just a double integral. So we know that this is going to be the double integral. And the rho in this case is xy. We can divide this into a type 1 or a type 2. So you can see that the equation of this line is just going to be y equals x, right? So from here to here, this is just going to be y equals x. So I can just do a type 1 integral. Okay, so I'm going to have dy first. This is going to be from 0 to x. And then our dx is going to be from 0 to 2. Okay, so that's going to be my mass. So I'm going to go ahead and calculate this guy. So this is going to be the integral from 0 to 2. Take the antiderivative of y, so that's going to be xy squared over 2 from 0 to x dx. So you're going to get x cubed over 2 dx. Take the antiderivative again. So you're going to have, so that's going to be plus 4. Oh, no, that's going to be plus 1, so it's 4. So on the bottom is 8. So you're going to have x to the 4 over 8 from 0 to 2. Going to plug in the 2 to the 4th over 8. Okay. And this is just going to give me, so 2 times 2 is 4, 4 times 2. Okay. It's going to just give me 2. So that's what I end up getting for my mass. All right. Okay, and now all I gotta do is now find the centers of mass. Okay, so remember, in order for me to find the centers of mass, I need to find my my moments. So let's first start off with the moments. Okay, so my moments, so let's start off with m sub x That's going to be the double integral over the region R of y rho xy dA. So similar, this is exactly the same integral. So from 0 to 2, from 0 to x, but now we have a y times xy dy dx. So you're going to end up getting 0 to 2, 0 to x, xy squared dy dx. Oops. So this is going to give me integral from 0 to 2, xy cubed over 3 from 0 to x dx. So this is going to give me, I'm going to pull out the 1/3. I'm going to get integral from 0 to 2. This is going to give me x to the 4th in the inside dx. Then you're going to get, when I take the antiderivative, you're going to get x to the 5 over 5 from 0 to 2. And that should give me 32 over 15. Okay, so that will be the moment around the x-axis. So the tendency to rotate about the x-axis. This is a quantified number. And now we're going to look at the moment in the y direction. So that will be the double integral over the region R, x rho xy dA. So this one, same thing, but now we're going to get x squared y dy dx. So this is going to give me 0 to 2, x squared y squared over 2 from 0 to x. All right, and then you're going to pull out the 1/2, 0 to 2, and then we're going to have an x to the 4th power dx. So we're going to have 1/2 x to the 5 over 5 from 0 to 2. That should give me 32 over 10. All right, so those were our moments. Okay, so now let's go ahead and find the center of mass. So center of mass, I'm going to write it as COM, center of mass. So x bar is just going to be the moment around the x direction. Oops, that's wrong. The moment about the y direction divided by m. So that's going to be 32 over 10 divided by 2. Okay. 8 over 5. And then y bar is going to be m sub x over m. That's going to be 32 over 15 divided by 2. That's going to give me 16 over 5. Okay, so there's my center of mass. Okay, so this is the point at which all the mass will be able to be balanced. So if you have a thin plate, this thin plate, and you want to find the balancing point, that's for the point in which the balancing point is at. Okay, so now we found our center of mass. Now we want to find the moments of inertia. Okay, so moments of inertia. Okay, so the moments of inertia, that's going to be I sub x, so that's the one with the squared. So the integral over the region R, so that's going to be y squared rho xy dA. So the setup itself is going to be the same, but notice that this time, because rho is xy, you're going to get xy cubed dy dx. And you can do this one on your own. You're going to see that this guy gives me 8/3. Same thing with IY. So you're going to take the double integral of R, x squared rho xy dA. So the integral itself is the same, but now in this case, you're going to get x cubed y dy dx. And again, you can also check that this is 16 over 3. And the moment of inertia about the origin will just be the sum of the two moments of inertia with respect to x and y. So 8 over 3 plus 16 over 3, that's going to give me just 8. Okay. And then finally, we're going to have the radius of gyration. Okay. So that one, we're just going to go ahead and just write down the formula. So r sub x, that's going to be the square root of I sub x over m. So that's going to be the square root, what was the inertia? 8 over 3 divided by 2. So that's going to give me 2 root 3 over 3. R sub y, that's going to be the square root of I y over m. So I y was 16 over 3 divided by 2. That's going to give me 2 root 6 over 3. And then about the origin would be I0 over m. That's the square root of 8 over 2, which is actually 2. Okay, so not the most amazing problem. This problem does take up quite a bit of time. And if the density is really bad, then it can take quite a bit of time. So this is how you would do this entire problem. I did skip a couple of things, but it's basically the same type of integration as before.